Tesla just proved its AI for autonomy drives 7 times safer than humans. No lidar, no HD maps, just vision. Tesla's AI learns directly from cameras to controls, just like a human brain. This changes everything for investors. Today, we're diving into Tesla Vice President of AI, Ashok Goswami's presentation on Tesla's end-to-end neural networks, the tech that could make full autonomy unstoppable. So what did Elon and Ashok mean when they said they're adding in reasoning to the models before end of this year? What did they mean that our cars will seem like sentient creatures soon? We have Phil Beisel with us today. Phil was a founding member of the technical team at Rivian, an electric vehicle maker. Before Rivian, he held various engineering management roles at Apple. Welcome, Phil. Thank you so much for doing this and taking your time for us today.
Hello, Herbert. It's a good one. It'll be fun.
It's a good one. No, yeah. This is an important one. At the earnings call, Elon and Ashok made some big statements. They're going to add reasoning to the cars. The cars are going to seem like they're sentient beings by the end of this year, just a few quarters from now. And then just a day ago, Ashok Goswami did a huge presentation. We'll put the link on YouTube if you want to watch that. And he talked about, I guess he explained how they built what they built, and you're gonna explain it to us in language that we can understand.
Let's hope so.
But just to start off, I'd like to show a portion of that video that he did, so we can understand what he was talking about, and then you can explain this part of it.
So you can see that this can update to scenes quite rapidly. If you use the same traditional splatting, a lot of novel views might look blurry or like fuzzed out. But as I'm rotating here in 3D space, a lot of the structure remains intact. And such interpretable representations can be used to debug the system. Like if it's going faster or slower, you can easily observe, okay, is it safely avoiding some obstacle or not?
So Phil, tell us what are we looking at here?
Yeah, this is the 3D Gaussians. It's really excellent. What's happening here is in real time. This is basically, think of it at the car level, is reconstructing from the 8 cameras a 3D space using these small pixel collections, these distributions, Gaussians, and it's able to do it with a high degree of resolution. I think is a good way of thinking about it. And as you notice, one of the cool parts is he really turns the scene around and he's looking back at the car. Obviously, the cameras aren't capturing that, but that shows the fidelity, or at least the intent of what they're doing in terms of capturing the 3D scene. In other words, they understand it from a 3D space point of view, which is just really excellent. Yeah, this part right here. Right, that he's panning around, or 360 running around, but the car's cameras are, this is coming from the car, that red car, and it's constructing that scene. Yeah, that's mind-blowing, and it's doing it in real time on the vehicle.
That's fantastic. So, okay, so you put together a deck, and you're going to explain point by point.
Let's
try. We're going to play some videos as well. Let's do it. I appreciate this. We love it when you join us, Phil, when you do this and explain to us full self-driving and all the technology.
Well, I'm super excited for 2 reasons. FSD, I think, has reached that level where we can say the checkbox on autonomy is there. We've checked the box. I've been talking about this for a year, seeing what I call convergence, like seeing where it's going based on each and every release in the 13s and coming into 14, and I think we've reached that place where they've actually done it. Obviously that doesn't mean it's a fixed stopping point. It's the launching of every other version that comes and so forth, and the thing will always get better. But I think we really are at that place as autonomy solved. Also, the other thing I'm excited about is for the first time, Ashok got to speak what's happening inside. I spent the better part of a year over 8 different articles kind of dissecting the stack from reverse engineering it, looking in, guessing. I got a lot right. I got some things wrong. A lot of that stuff has been corrected over time, but it's really, really awesome to hear him speak. And it also gives me a sense that they are just so far ahead. They are so far ahead of the competition. I'm not even sure there is competition, to be honest with you. This is outside of things like Waymo, which take a different approach, and we can talk about that, they have solved this in a particular way that's very, very scalable on the lowest cost hardware possible, which basically means every one of our Teslas, in terms of an inference stack and just kind of cameras. I'll call them off the shelf. Obviously, it's a little bit different than that, but we're not using very heavily tuned sensors here, and we're not doing those kinds of things. This is a vision-based system. And the other thing I'm excited about, maybe you can jump to the next slide right away here. I'm also excited about the fact that he has leaned in and told us that this is the unified architecture. This is this stack, this entire stack is not just solving the FSD problem, it's solving the Optimus problem. And in this particular slide, I'm referencing on the right an article I wrote about 2 weeks ago about this very topic, the unification. And last week, in your absence, CERN hosting and I did a show on this, which I definitely think readers or viewers should take a look at, because it kind of goes into what is this unified thing. And for the most part, I feel like it's right. There's some little tweaks I'd make after hearing Ashok speak, but generally it's on topic. If you look to the left, that's a slide out of his presentation to the ICCV, where he's showing Optimus' view of the factory, reconstructing this in simulation inside their simulator, real world simulator. So in other words, this isn't a vehicle, this is Optimus, right? This is a view, original, the simulator trained on images taken from the data set of Optimus, not full self-driving. So that's very cool.
Yeah, fantastic. I mean, people should watch that video, because you already were one step ahead. Not you're not a step ahead, but because obviously he's
no, I'm not a step ahead.
Just,
I'm just yeah.
He's just presenting it now ahead of you, but you presented it earlier.
Yeah, I'm like, I think I got it right. So
you got it right. People should watch that. So the key thing, the key question, and I want you to answer today at certain parts of the presentation, you don't have to do it right now, is many people think, oh yeah, Tesla's got simulation, they got cameras, this is repeatable and copyable. Some people have gone out and said, oh, every car maker is going to be able to copy this within 6 months, 3 to 6 months. And others say, well, with AGI, you can just take simulation, and NVIDIA's simulation world will be able to replicate this. So you just said this is something that they're miles ahead of everyone else. You can explain that as we go through.
Yeah, let me give you a few comments on that really quickly. I'm not going to treat the AGI thing because that's silly. That always just says there's some future thing that will solve all problems. And, sure, that's a reasonable sentiment. That's a reasonable thing to say. But there's no proof that anybody has gotten there on that. So it's really a waste of time talking about the AGI thing. In terms of being miles ahead, and I mean, first off, if you go through, and I did carefully, everything Ashok said is he didn't tell you what's in the box. He didn't tell you what the secret ingredient is. He didn't tell you the layout of the neural network. He told you lots of things about he characterized it in various ways. He characterized their design philosophy, but he talked about sort of the architecture from 50,000 feet, but he did not tell anyone how it's done and what the internal architecture of it is. So it's really important to make that distinction. He did not provide any blueprint. He just said, this is what we're doing. Other people will want to follow the basic idea, certainly. That's one point. The other point is that we have to recognize that he talks about the long fat tail of driving scenarios in autonomous driving. And it's literally insane. It is the longest tail problem I've ever seen in computer science. It is, and the only way to solve that is, as he mentions, that we, Tesla, have the Niagara Falls of data. We have so much data the real problem is figuring out which data is meaningful and useful to them. But what that means is whether you can do simulation or not is quite irrelevant if you can't tee up the scenarios. you can't pretend to tee up every possible scenarios. He puts some on the screen that I think most in the video and the presentation that a lot of people would say, I don't know, I never saw that when I was driving a car. Those things present themselves every single day that we're driving, and they're collecting them, and no one else can really do that. Even if you've got the perfect real world simulator, tell me how you're going to load it up with the right number and the correct types of scenarios. It's very difficult to do that, I think.
Yeah. So I think he said that every single day is something like 50 years worth of driving
500
every day. 500 years of driving
I believe that's
in
correct.
one day.
Yeah.
Okay. And then he said before previously, and I think he's saying it here, which is, okay, let's say that we want to solve what would the car do if debris falls off a vehicle in front of you? He goes, well, we've got the data. So we would just, ask, give me, 10,000 video scenarios of debris falling off of vehicles in front of the car. And then up it comes because they've got all the data, and then they train the car on that. Now, how would any other car company be able to do that when they don't have millions of vehicles driving now, capturing all these different edge cases, right?
It's really hard to design the edge cases. It's very hard to design them. It's better to get them as templates into the system. That's essentially what they're doing here, right? They're taking these edge cases that they curate, they find, and they're bringing them to the system as templates. And it's very hard. Otherwise, you have to invent that template yourself. Let's jump to the next slide, I think. Yeah. So now what I want to do here is I kind of want to go through his presentation. I want to kind of parse it using my language and try to simplify it a bit. It was really excellent, but sometimes it gets a little bit deep. So maybe we can keep it.
Please.
Keep it easy.
Thank you.
Anyway, he not only did a presentation at this conference, the ICCV, but he also put an article up on X last night that most of us have reposted. So it's worth taking a look at that article. In fact, I think the article in some ways is better because it's you can sit down and digest it at your pace.
Yeah.
All right.
We'll put a link to this as well, and then we'll watch these videos that he posted here and explains things as well. So, thank you.
Okay, so what he starts off is he says that we Tesla. Every time I say we, I'm referring to Tesla and not me.
Yeah.
Other than the fact that I'm a shareholder, I'm not there. That Tesla is building a foundational model, right? That they're building a vision foundational model, and that it is importantly an end-to-end model. So what that means effectively is that it is trained end-to-end. In the interior of it, there's some modules, and we don't know what that interior looks like, but it's important to recognize, and which we'll talk about it later, what end-to-end training means. So on the left side, we have all the sensor data running through the system, and on the right side, we have the control outputs, which he labels as next action, which simply means how are we going to actuate accelerator, braking, and steering angle in a vehicle, right? Okay, let's jump to the next slide. So he's making the case here on the left hand of this of why do end-to-end? And by the way, end-to-end is a specific thing in AI here. It means that they've trained the model end-to-end as a unified thing. They haven't trained components of it, assembled them with interior logic. They've really run the training through the entire thing. So what he's saying is that codifying these what we call human values, and that's not numbers or values, not referring to numbers, but rather more or less behaviors, is really difficult. Like, how does a human make a value judgment on whether they should avoid an obstacle by accelerating and steering around it or braking? And lots of humans will do it different ways. And it's very difficult to codify that into simple kind of, if this happens, then do that. And he presents that in the small video where he shows a vehicle. It is on a two-lane opposing lane highway. There is a large puddle, and he's saying, what should we do? What's better? Do we go over the puddle itself, not knowing really how deep it might be? Or do we go into the oncoming lane and avoid the puddle? And
Can I show that video?
yeah, I
And
think
then
you can find that.
that's the one on the top right, right? So
It
let's watch
should be
that video,
close. It should
and
be close to the top. Yeah.
yeah, and you can explain it as it's playing. Let me move it to the beginning again. I think it's in the middle here.
So here we see the puddle, we see the car. What does it do? It goes into the opposing lane
Yeah.
to avoid not just one, but two puddles.
Ah,
And it sort of waits and does it for the third, and then it kind of comes back in.
gotcha.
It's probably what you and I would do.
Yes.
It might not be what everyone does, but that's basically his point, that if we tried to do it from a logic build out, we'd probably say, well, the rules of the road suggest that we shouldn't go into the opposing lane. Well, what's happened here is the vehicle has recognized through its neural net that there's no reason that it cannot go into the opposing lane because there's no oncoming traffic or obstacles. And therefore, it's safer to do that than to go over a puddle where the car could lose traction, or actually you don't know what's under the puddle, right? You don't know what's at the bottom of that. You don't know how deep it is. You don't know if there's some other obstacles that you can't see. So, magic, right?
No, I love it. I love
Yep.
that so much because that number one, that is what humans do, and you can't codify it. That's what you're saying. If this, then that. And then this is the thing: is like, remember when we first did that first ride with Robotaxi, and I think it was Rob Maurer. He was testing Robotaxi, and the car decided it was going to turn left, and they said, "Oh no, it's actually I shouldn't turn left there. I should go forward," like many humans would have done. And then it drove in the wrong lane for a while.
Yeah.
Everybody, the world, the news said, oh my God, Teslas are dangerous. But there was no one around. And that's what we would have done anyways. It's not dangerous to go on the opposite side if there's no one around. If there's somebody coming, then that's dangerous.
Yeah.
So,
Well, it's easy to criticize a robot in the case of following the rules with some rigidity. But the point about driving is if you follow the rules with rigidity, there's certain things that are true. One, it's not necessarily the safest path. And two, it's certainly not efficient or human-like. So, both those things are true, and they're able to do that. That's what I think people will see when they think about a Tesla. It will not feel like a robot, as I think Elon says, it'll feel sentient. What he means, I think, effectively is he means like it feels like a human is making good driving decisions in a very fluid and dynamic way. With full safety in mind, right? So that's it. That's yeah. So in addition to that, he's saying, why don't we make a case for end-to-end training of this neural network? And he suggests that the boundaries, the interfaces between perception, prediction, and planning are very ill-defined. And the example he uses is this two scenarios where he shows chickens crossing a road, and then he shows geese, in a sense, in the road, and they're not moving, right? And the car does the right thing in both cases. So here's I think you said starts with ducks and ends with chickens, but you can say,
no. It
I
starts
think you're
with,
right. Are they chickens?
no. Yeah, I don't know if those are ducks. Yeah, there's ducks. Ducks are crossing,
Those
and
are
then there's
ducks.
chickens here.
And there are chickens. I mean, who knew we'd actually be talking?
The chicken could actually cross the road. There you go.
And by the way, there's one still coming. Look.
Oh yeah.
That's why the car's waiting.
Gotcha. So, first of all, recognize that that car stopped too. First of all, great. Let these guys cross, and then it knows the intent, not only of humans, but in this case, animals.
Yeah.
And the intent is they're going to cross the road and it stopped appropriately.
Yeah. And so, and then look at the next video. This one, obviously from a user on version 14, showing the car coming into parking lot. There's geese standing in a puddle. The geese aren't moving. The car takes a different piece of behavior. It's not waiting endlessly. It waits a little bit, but look what it does. Backs up, goes around. So if you were very rigid about how you thought about the perception side and the planning side, you'd never make these different decisions easily in the stack. That's why he's saying end to end, because you would say, I perceive essentially the same types of things. Obviously, part of perception isn't just object perception; it is intent, motion. But that said, he's still saying, look, if you make a block over here that is completely about the perception, figuring out what's there, and how it's moving, and then you go into the planning phase, what are you going to do about it? You probably aren't going to make that distinction, especially if things like our chicken example, you have a late, like the late guy coming across the road, right?
Yeah.
You may have thought he was going to be stationary. So in this case, he's saying by training it end to end, we can avoid those problems and make the system more fluid.
This is an example of intelligence, not just, more LiDAR will solve this. You have to have the intelligence.
Intelligence, I mean, obviously, I think they've proven, if anybody's confused, I think they've proven that vision works. Vision is a sensor that works. There are a lot of scenarios that we haven't seen tested, but I suggest that most of them are going to work pretty well. If you watch those 3D Gaussian views, you realize that they pretty much can reconstruct the space. And now you're left with, well, if the sensor set can do its job, can the brain do its job? Then that's what, they spend, in a sense, if you think about it, they spend most of their effort on the brain.
Yeah, which is the right thing to do. Would you rather have a third eye, or would you rather have a bigger brain, a smarter brain? Okay.
True. And they have 8 eyes to start with. So
That came from you a long time ago. Okay, let's keep going. That's fantastic explanation. Thank you for that.
He also wants to training it end to end. He also wants this. You can go back previous slide. Yeah. He also wants this homogeneous compute. And what he's trying to say is, I'm running a real-time system here on the car. I've got to do 36 cycles, at 36 hertz. I've got to run this thing. I want to have a deterministic latency in the system. And by pulling it together as one neural net, I have a better sense of that. And then lastly, he's saying, hey, guess what? I believe I'm I'm on the correct side of the so-called bitter lesson, if people are familiar with that. It's essentially saying that, bigger models and more data equals better performance. And I note that there. Let's jump to the next slide. So now what he's getting into is, okay, if we're going to build an end-to-end network from pixel to control, what are the challenges? And there are 3 areas that he talks about: the cursive dimensionality, interpretability and safety guarantees, and evaluation, of which the hard one is number 3. They're all hard. But the real hard one's number 3. So let's talk about each using his very slides. So the cursive dimensionality is sort of it's really what it's saying is we have a lot of data. We have a very, very large input. If you look at, I wrote on the far right, 2 billion running to 2. It's essentially what the neural network is doing on each cycle. It's taking 2 billion input tokens and converting them down to 2. What are the 2? Steering angle, and then there's a negative and positive for, acceleration, which means that if it's negative, probably applies brakes or some version of, So what is the input here? Well, he talks about it. He says, we have this input context window of 2 billion tokens. We have 7 cameras. They're running at 36 frames a second. The size of them are 5 megapixel. We're running a 30-second history loop each time. Yeah. And then he's saying we're configuring it as a 5 by 5 pixel patch. And essentially that's kind of saying that the pixels are in 5 by 5 clusters. And then he's adding, okay, but that's not the end of the data. We have navigation route data. We have kinematic data, which is the IMU. We've talked about that in the past, probably GPS. And he also talks about bringing in audio data at 48 kilohertz. And then essentially, what is he saying the output is? It's simply the steering accelerator. So that's a very high dimensionality problem. And that's essentially saying, well, we're stuck with the curse or the high quality problem of high dimensionality.
Yeah. So first of all, this is interesting. He said that the navigation maps and route for next few miles. So I've always wondered about that. Like, it's like the car actually knows using the navigation maps where I'm headed, and they pre-map it as I'm driving. And then if other cars have driven in that space, it uses that to understand that, how to drive in that, upcoming left turn or whatever. And then this also speaks to the fact that that's 7 cameras. What happens when you add a lidar, when you add all these radars, when you add these other things? It's like exponential big dimensionality, right?
Certainly there's challenges running this on hardware 4. They've indicated quite directly that hardware 4 is sufficient to run this model and more, but not too much more. And we'll at the end of the presentation, we'll probably talk a little bit about that. But I think the important thing to hear based on routing is to understand that there's a clue here, a 30-second history window. So it's not just taking the data in that particular instance of that cycle, but it's also the history data as well, which may be compressed in some particular way. But part of that is, a forward lean and what you've seen in the past. And then, of course, the other part is what's upcoming in the route. What part of the road segment are you actually supposed to follow? Because if you're 500 feet out and the car can see it, and it's supposed to take a left-hand turn based on routing, it's starting to put that into its planning cycle at that point, right?
Yeah.
And that's an important thing. It's not like it's just comes upon it and instantly makes that decision. And that's why the routing data is kind of constantly plumbed through the system along with the sensor data. So he goes further when he's talking about dimensionality, saying, well, guess what? Within our fleet, we accumulate about 500 years of driving data every single day. I don't know how he bases that, but let's just assume it's true for sake of argument. And what that means is that any given car or aggregate across the fleet, there's just too much data. There's just too much data. So what do? And they have built a lot of little things to make it so that they can select the right data. They have in-vehicle, part of what they do is they're triggering. They have a set of triggers that they say set these up to trigger on these kinds of conditions so that we can package and send this data. They built tiny portions of their neural net capture these corner cases as well, like emergency vehicles. They probably capture, it's like, oh, I hear the sirens or I see the lights. Those are things that they can kind of command the car to be in this mode where they're sending these samples. They can certainly, whether they're in shadow mode or running, is that they can evaluate the prediction versus what happened in hindsight, right? So when something goes wrong, that's
Yes.
a piece of data they want to accumulate. Now think about what we did when we circle back to the beginning of this presentation, where I said you want to set up scenarios that are these crazy driving things that are very hard to just kind of, if you've got a simulator, just load up in the simulator. Well, how are you going to know all of these things? Well, the car is actually, in the slide is saying that in the car, what they're doing is that they're actually have built a lot of logic to determine how to select that data. And the last one he mentions is any large state change in the space, what he calls state space. Like what he means is if the scene dramatically changes in some way, and he doesn't characterize what dramatic change would be, but any large change, he's saying, okay, that's important that we. So it might be like an object shows up instantaneously, like a pedestrian darts out into the intersection. That's a big change in the space, and they would probably mark that. Remember, what's happening here is that they're collecting these little data sets that, the previous slide talked about the kinds of input data. They're collecting those data sets and they're running them through the system in real time. And some of them, based on the criteria that they've established here, are pushed off to flash storage for later upload when the car stops and you get back on your Wi-Fi, and then they build a package of data that they send to their training center. So that's another element, is that they have a lot of data that it's a curse. It's also a blessing.
Yeah, curse of too much data. So this is all of us driving all of our cars, even if you have FSD or not FSD, it's driving around, it's got the 7 cameras and it's capturing everything.
Yep.
And so this is where when people do disengagements, and when we've been testing FSD, us beta testers who've been testing FSD and you disengage, that is a trigger, could be one of the triggers that they're grabbing. It says, okay, every time that they disengage, let's grab that and we'll run the neural net on it to see what happened. And then they can also do their own, I think the next 6 months, but let's track every time any car ever sees an emergency vehicle. Let's track that, grab that data, and then we can use that to train.
Yeah, and I think, Herbert, I think they can turn around tomorrow and say, here's another scenario we want to collect. They push a set of, I'll call it marching orders to the car that then says, okay, let's start selecting, we've had some problems with separation off of bicycles and bike lanes. Let's pull data that's, okay. Yeah.
Anytime there's a bike lane, capture that video, send it to us, and then all of a sudden the fleet that's out there grabs it, sends it that night.
Yeah.
They got data.
And And then they get a lot of samples, hence the curse of dimensionality.
Love it.
And by the way,
Yeah.
I would say that the human intervention is probably the least interesting now. I think it was interesting back in the day. I think
Yeah.
it's the least interesting data
At this
collection
point.
point for them.
I agreed. Thank you. Okay, so tell us what we're looking at here.
Well, these are
that's, I think,
these are just different samples they've collected where, I mean, these are real samples. Yeah, here's the guy going backwards.
Shit.
Yeah.
Oh my God.
Yeah.
Yeah,
So
it's repeating.
these are real samples that they have collected from the fleet. Now imagine, just sake of argument, just any one of those where a kid comes across and the person's walking the street. Imagine the behavior is slightly different.
Right.
Is he walking? Does he turn around and go back? That it's very hard to do that by assuming you can just guess at all the real world stuff that happens. It's better to collect it and use it as an operable template in your simulator.
Yeah. So they can go, send me, 10,000 variations of a human walking across the street in front of the vehicle. And
Yep.
then from there, they can learn what is
Yeah.
the human intent. Is this guy really intending to cross? Is he pausing? Is he
Yeah, they
waving
can-
you away? Is he saying, screw you? Is it going to come attack you? Is it going to, whatever, right?
Yeah, there's a lot of things that, I say it over and over again. You can't guess these things.
Yeah.
If you really think it through and you say, well, show me, write down all the scenarios where pedestrian crosses the road in an inconsistent way, not, legally. Good luck with that. It's easier to collect the data, and they have such a torrent of data that it never ends for them, and then therefore they're stuck with the curse of a large data system, which they have learned to use to their advantage effectively. Yeah. All right, let's keep.
And I mean, you and I are driving and we're humans and we've learned through our years of growth, experience, what we think. Oh, that guy's a drunk. He's drunkard. He's walking weird. He doesn't have the state of mind to know what he's going to do. So I don't know what he's going to do. He could be very erratic. So I'm going to stay away from him. Another one is, I can see that person has an injured leg and they're hobbling. And so I'll slow down and stop and help them maybe or something like that. But
you might not see to the person turns to face the car that maybe, they're actually a construction worker. You may not know what they're trying to stop the traffic, and all of a sudden you see, they're holding a sign.
And that's where the signs and because we always wondered when the guy goes, stop, and then he goes, okay, go, or whatever whatever things are. We know that means we're supposed to go, and now the car knows.
All right. So now he jumps into this second challenge, which he calls interpretability and safety guarantees. And what he's saying is that this foundation model has many interpretable outputs, right? And these things that he writes down here, 3D occupancy and flow. Occupancy means like what's in the 3D space. It doesn't mean what's in the car. It's not related to occupants in the car. It just means what's occupying the 3D space outside the car. What kind of objects are there, and then how are they moving? And so then they clearly identify these objects: vehicles, pedestrians, bicycles, as he mentions, identify things like traffic controls and road boundaries and lane, and all the semantics involved in that, speed limits and other attributes. And then he's saying that that we can effectively output our decisions in plain language, which we are going to talk about in a minute. So let's jump on.
That's okay.
So here's a pretty interesting slide when you start to think about it. He's saying, here we have this big neural network. And as we described before, each cycle we have about 2 billion input tokens. And we're really interested in outputting 2 tokens, which represent essentially accelerator and steering angle. But then he's set this other stuff here: panoptic segmentation, 3D occupancy, 3D and Gaussians, language. What he's saying is that there are these intermediate outputs that come out of the model, and he puts them into this box called reasoning. All right. Yeah, so
Yes.
we're going to talk about reasoning later, but it's important to recognize the basic point of this is to say that while this is an end-to-end neural network, it does not mean it's opaque in the sense that all we can see is the input data and the output controls.
Mm.
We also get these intermediate values that gives us the opportunity, us Tesla, the opportunity to both debug the system and add a real-time reasoning component. That's the point of this slide. Let's
Gotcha.
move to.
Yeah, it's like when you do an LLM and you ask it a question, it can actually show you its the chain of thought. It says, I'm going to
Yeah.
first do this, I'm going
This
to
is-
do this, I'm going to do
right.
this. And then you go, oh,
Yes.
why did you do that step? You don't need to do that step, and or whatever it is. You did that step wrong. Yeah. Okay.
Next slide. So this is two follow-on slides where he's talking about interpretability and safety guarantees. And on the left, he's talking about this whole, what he calls 3D construction of the space through these, what they call Gaussian splats, or like little, think of them as little color blobs of distributing the input photon spectrum, okay? Gaussians are kind of like just bell curve objects, if you will, and splats are sort of like, instead of thinking of it as a discrete pixel, think of it as kind of a paint splat assembling a picture. And he's saying, well, we do this on the vehicle in real time. We can generate this in 220 milliseconds. We don't need to do these other types of things that the hard part of this problem has traditionally seen. So they've developed some IP in this space that allows them to do this on their hardware effectively, and that allows them to interpret the scene better by reconstructing the scene properly, is essentially what it means. And we started off showing a video of just that, where the red Tesla runs through this thing and we could see the whole 3D space on the, sorry.
Yeah. Well, why don't we play the videos, or do you want to?
We can keep going. I think
Okay.
the one on the right is super interesting. It's very hard to read that here in my presentation, but you can certainly look at his presentation. This is where it is literally they're able to interact with the system and create high interpretability. So you can actually ask the system, why did you do what you did? And it can tell you why it did what it did. And think about that from just the point of view of debugging the system. People always ask this question is, when they see an incorrect behavior, what did they do? Well, they can load that data sample into their simulator system, and then effectively looking at this, looking at the interpretation on the right, they can ask the system, why did you do what you did?
Hmm.
And it can go through it. Yeah. And that's not just important for debugging, but we'll see that is critical for what is to come with reasoning.
This is amazing. Like, you can basically talk. That's what he means by this is a sentient creature,
Yeah.
because you could actually talk to its thinking process, and you could.
Yeah, this is amazing, because it's essentially saying that they essentially have their own, call it mini language model, trained
Yeah.
to the intermediate outputs of the model that can be both interpreted in real time, but also reflective of the plan. So there's a lot there. And, he calls that natural language can help us in system to thinking cases. And what he means by is, looking at the overall system, we can both debug it, look inside and figure out what it did. So again, it's not opaque, even though it's end-to-end trained neural network, it's not opaque. It can be pulled apart. And then we can also do some, special stuff in terms of what we'll talk about in a bit reasoning later.
And also, I imagine this is where you can actually tell it what to do, right? Can you go, hey, don't drop me off here, please. Drop me off behind the mailbox. When I'm being driven home by a ride-hail service,
Yeah.
I always tell them, you don't have to go into the driveway. Just park me right in front of the driveway. That's good enough right here.
That is what we will talk about on the very last slide on reasoning. Yeah, we'll talk about that.
Nice.
All right.
Okay.
Now he goes into the third challenge, and he calls this the hardest of the three problems evaluation. And essentially, what is this? This is attempting to figure out what should we do, essentially. What is the thing that we want to do? And he says, even with high quality data sets, simple loss isn't a sufficient indicator of performance. That's a very specific thing he's saying. He's saying that if we build a simple loss function, people that understand training of neural nets understand the concept of a loss function. It helps establish the parameters through backpropagation, yada, yada. But the idea is he's saying in this system, to get a nuanced, sentient kind of driving experience, we can't just do a simple loss function. A simple loss function would be sort of like, did it follow the rules of the road when it was not supposed to go into the opposing lane for the puddle, right? But we've got a different thing going on there. We have to evaluate it. And what he's saying is a tool for this is that instead of using what we call open loop performance, or said another way, he's saying that in order to do proper evaluation, we in effect let the car drive. The car is in the loop. The car is part of it, and most of this is done in simulation, right? So they are a lot of this relates to reinforcement learning. My article talks about reinforcement learning. It's a very important part of what they're doing. They're setting up scenarios. They're letting the car drive those scenarios in simulation. And from that, they can evaluate the performance of the model based on that. And, so there's a lot to that. The article explains how it does proper rewarding and penalties associated with it. But he's basically saying this is the hard problem to solve. And one of the ways we solve it is we let the car drive it in simulation.
Let it fail, then say, nope. Let it fail, nope.
In a closed loop system, which means essentially two things: the car, the ego, the thing is part of the. It's not just like do one cycle and deter. It is the car is part of the drive, and then they let it drive for a period of time where they're feeding back over time. So it's a very important part of how they determine whether they've made the right decision, the evaluation component. I think you can jump to the next slide. Yeah, so again, what he's saying is kind of what I just said, neural network closed loop simulator, right? So you imagine a simulator, imagine you put the car in a scenario, maybe one of hundreds of very similar scenarios, and you can train it with what they call cheap to collect state action data, which means that they've brought the data to bear. The system can generate it very quickly in simulation, and then they can run it through a time cycle. Notice how he's saying time plus one, t plus one. He's essentially saying we're going to loop it through, and it's closed loop because it loops through over time, and the car itself is in the solution set. And what that means, if you kind of go back to basics on reinforcement learning, is that they can run thousands of trajectories. Like we saw the person walking across the street. And we said, well, how would we manage that? This is just showing the simulator. By the way, everything in this scene is simulated.
Isn't that crazy?
Yeah.
Yeah. It is real. It is.
There's no way. Yeah. Now, mind you that, again, Tesla advantage. What they have here is they didn't simulate this out of thin air. They took a piece of real world data. They brought it up as a template. They subtracted the objects from the template, and then they added back their type of objects here. So what's cool about this is not only is it they can do anything they want now in the simulation, right? They can change the traffic light configuration. They can make the green go to red instantly with no yellow. They can remove the double yellow, like a newly paved road that doesn't have, no one's painted the lines yet. They can remove all of that. They could put a large sinkhole or pothole. They could add countless pedestrians walking through the scene in unpredictable ways. You name it. That's simulated.
This is the crazy part. So what we're watching here looks like real video, but this is actually the Tesla's world simulator. And so when people say, yeah, NVIDIA has their own simulation engine that they're going to rent out or sell to other car companies, everyone can make simulation and that's how they're going to beat you. Well, the way to make real world simulation is to use real world data to be as accurate as possible, to have all these different scenarios, edge cases. You still don't have that. So, this is great. This is what Elon means when he says that no one has access to this data. Like every AI company has access to all the data that's ever been produced on the internet. They've got all the data to YouTube, let's say, all those videos, but
Yeah.
they don't have real world data. This is data,
Correct.
video of what's happening in the real world. Same thing's going to happen with the bot, all the video that the bot's going to generate. And then from there, you can create these high fidelity simulators that can then create millions of scenarios. You got to start with this videos, and Tesla has
Yeah,
what,
you start with the raw data set.
cars.
You use it as a template. You essentially, because the system kind of is introspective, you can remove the objects from it and place new objects within the scene. And then what you can do in terms of say reinforcement learning scenarios is you can then go and set up the agent, the car is the agent, to run thousands of different trajectories through that light, that particular intersection, and score them and essentially train the system on the outcomes that are preferred.
This is it, right? So here's a new policy. So they've created a new model. It says, hey, we created a new model, updated a new version of FSD. Let's see if it works better. This is the original. And this is how the new driving decides.
So
can you tell us what's while watching?
What he's saying here is we are going to take kind of a new policy that we've put in the system, and we're going to reevaluate old training sets, running them in our simulator, and we're going to score them again to see how they behave, or put eyes on the problem as well. I mean, there's times when engineers will put, but see what's happened here is in the let's say on the left we're looking at version 13.2.9 or something, and the car goes too close to the person walking the dog, and then and maybe 14.1 on the right hand, they've retrained the system, and they can go and make that evaluation and determine. And if you play it, you can see it gives it more burn.
Yeah, drive further away, which is great. So isn't this great? It's like even just little tiny things like this. Okay, it's one thing for you to say, hey, if you see pedestrians, give them room. But then here it's like, give them a little bit more room than we used to give them, especially in this scenario, specifically in this scenario where there's no one on the left.
You know, this can be, in this particular case, I think they're pulling a real piece of data, the system, meaning some driving piece of data, but they could also build that in simulation.
Yeah.
Mm-hmm. So cheap to collect data, right? I mean, they have a lot of data. Next slide.
This is the next slide now.
Yeah, here we go. So we saw the one on the left.
Yeah.
That was what we call reevaluation. And then the one on the right, in evaluation, saying evaluate policy models on synthetic adversarial issues. So can you play that video? It's the one right after. Yeah, watch this. Now, on the left-hand side, that's what they captured. On the right-hand side, in simulation, they took the car that's on the right, and they made it cross through the lane.
Yeah.
That's all simulated.
Look how it's basically real, because the one on the left is real, and the one on the right is simulated, but it looks exactly as if it was real.
So they created, what they call synthetic data, and they set up this, what they call adversarial issue, meaning an issue that they considered, dangerous. The car comes across, and how's the car going to react to that? They can either look at how the car reacts to it in a current model, they can reevaluate, or they can use it for training in terms of their reinforcement learning to see how the car, to set it to behave a certain way, which is pretty awesome. All right, so let's go back to what happened at the earnings call a couple days ago, Wednesday of this week. Let me read this. This is Elon speaking. We've released 14.1. We have a technology roadmap that we think is pretty amazing. We'll be adding reasoning to the car. Mm-hmm. Our world simulator, which we've just talked about for reinforcement learning, we've talked a lot about reinforcement learning, is pretty incredible. Our Tesla reality simulator, when you see it, the video that's generated by Tesla reality simulator and the actual video looks exactly the same. We've seen examples of that now. That allows us to have a very powerful reinforcement learning loop to further improve the Tesla AI. This car will feel like it's a living creature. That's how the AI will get. That's how good the AI will get with AI 4 computer before AI 5. And then he talks about AI 5 being, 40 times better in some scenarios, just calling it generally a 10x improvement. So now here's Elon saying this. 2 days later, Ashok releases really what is complete evidence that supports this statement, showing that that's exactly what they're doing, right? And what I wanted to point out in this particular slide is called FSD Reasoning. I want to talk about reasoning and what that means. The most important first step in reasoning in a model like full self-driving is that, in fact, it can generate these intermediate reasoning tokens. That is, the things that tell us what the interior of that model has done. Remember, I said a few slides ago, if you train an end-to-end neural network, the danger, the thought, the reason people don't like to go there is because then it's opaque. They can't see inside the box, so they can't understand what the box is doing. And to tweak the box, all they can do is potentially retrain it and look at the outcomes and say, did that work? But now, what the technology they've developed is that they're generating these intermediate reasoning tokens, meaning all these different states that say, what did the scene look like? What did the 3D scene look like? What were the objects? Where are they moving? And in addition to that, I call it a mini LLM, that they have effectively their own little natural language processor in there where they can be introspective, either from a debugging reason or from a adding features in reasoning. Let's jump to the last slide, and I think this will close the loop on this discussion. So this is largely the same slide I presented last week with CERN on your channel. I've added a few things in here, and I call this the inference framework, and this is true of the inference framework on FSD or Optimus. Okay, they're largely the same. The sensors are largely the same. Cameras, there's a difference in numbers, probably resolution. They're taking in IMU, potentially GPS data. In the case of Optimus, they're taking in touch sensor.
You can have the tire sensors. The tires are to touch.
Yeah. In the case of Optimus, they've some type of touch sensing, and of course, an audio stream, right? Listening to the surrounding. And the top box is the thing we've talked about in this entire presentation. And I call it the action AI. Essentially, it's the stuff that Tesla's developed. You might want to call it the vision AI. It is the thing that takes that sensor data and outputs controls. In the case of FSD, we know what that is. Ashok calls it two tokens. It dissembles into steering angle, accelerator, and braking. And in the case of Optimus, of course, it's a bit more complex than that, right? You've got full actuation of arms, hands, legs, feet, body, head. Yeah, there's a lot more going on there. But essentially,
million actions. Yeah.
It's the same AI. It's obviously a different training. It's not exactly precisely the same, but the architecture of the AI is very similar. So, however, I've added this little piece in here called reasoning tokens. And what I'm suggesting is, as per Ashok's discussion, is that intermediate reasoning tokens are being emitted or from the actual inference cycle, and that allows you to push it in various directions. And one direction is you can push it down into the interactivity AI. We'll talk about that in a second, or you can push it back through the action AI itself. Right? The interactivity AI is something that's not quite there yet. But that's where we're going to add, Tesla, will add full voice control to the car from the human. Wait for the human to interact with the car, or the human to interact with Optimus, right? And that will be technology that will come from XAI, both from text to speech, speech to text, as well as the interpretive component, the LM component, if you will, of that very speech. But important thing is, as per our discussion earlier, you can get these reasoning tokens and you can push assembled instructions back into the inference framework to do things. And your example, I think before, was sort of like, oh, please park here. And in talking to the interactivity AI, the car may ask you, do you always like to park in a corner spot? And you could say, yes, please record that as my preference, or yes, and the car will record that as its preference, and then can push it through the system. So essentially, you would think of it as, and you can think of, any kind of intermediate instructions. Guaranteed, obviously, the future of robotaxi is a voice interface from the customer.
Yes.
drop me off here, as you suggested. No, a little bit. Imagine you say, drop me off here. The car pulls over here, just like when no, just the next house up. Car moves up a
Yes.
little bit. And
Yes.
then, why does that become more sentient? Because what happens is the car, the stack records that interaction, that behavior.
Yes.
It codifies it into some kind of, language of control and preference that's associated with your account, your robotaxi account. So then when you go into the next robotaxi 2 days later and you have it, you say, yeah, drop me off in front of my house. That is now part of your profile, and it's injected in this sort of reasoning aspect to direct the car to do something very specific that before you had to tell it all these steps, and now it's remembered these steps.
So does the car have memory, Phil? Like, so in my car, in my driveway, first of all, it's never driven my driveway. I'm expecting a version 14 when I get it soon, today. It's going to be able to drive in my driveway now. It's a curvy driveway. But will it remember that my car, I wanted to park it on this garage door, but my wife's car parks it on this garage door? Does it remember that my preference when I go from my work to this restaurant I go to, I want to take this specific route, not that route that the maps would say?
Right. Yeah. So the answer is I do not believe that there is much of that in today's 14.1.3. I think there's a few things there, but I think a lot of that's coming,
Wow.
and that's what I think, when Elon said, I think in 14.2 or 14, we've got a healthy roadmap, we've got an aggressive roadmap, we've got a fun roadmap, whatever his words were, and we're going to add these reasoning components. I think that's essentially one of the things that we're going to look at and say, these are things that make the car seem rather intelligent because we've directed it to do something that it then remembers. I think what's important to remember here is it isn't really necessarily associated with the car. It's associated with you and your profile. So, it may be that the car behaves a certain way when Herbert's in it and another time when your wife is in it. And it's really because she's in the car, it codifies her preferences and runs them through the reasoning engine. And when you're in the car, it does it differently. And that is what I was saying earlier, is that your preferences will travel with you through all your different robotaxi experiences. So pickups at airports, you want to be picked up in the arrival section. You always come in on United at San Francisco. You always want to be picked up in departures, not arrivals or something like that. And so when the car comes to pick you up,
Yeah. Oh, my wife complains all the time that she doesn't, when we're driving on the highway and we're on FSD, before it used to ping pong a lot, switching lanes and all that. And so I had to switch it to chill mode when she's in the car because she doesn't like it to switch. I find it to be too slow. I want to use Mad Max. I want to use Hurry, but we settle on standard. And so, yeah. And when she's driving the car, learn the way she wants it, which is don't, take it slow, be safe, she doesn't mind, right?
Yeah, and what's important to recognize about those modes is they're a collection of smaller types of inputs that are going through the model. Like Mad Max is probably 20 or 30 different things of how does it change lanes, what kind of speed, what kind of offset. So for example, you might like 9 out of 10 things, but the one thing you don't like is its offset to the vehicle in front of you. And you could then talk to it and say, I just feel like you follow vehicles too closely. And the car will say, okay, I'll,
just that part. Yeah.
I'll adjust that part. Yeah. So those, they've created these large sort of boxes of modes, but within that, they've got all these little teeny granular types of controls. And you never need to, like in the past, you'd have to see them exploded into some interface and a whole menu and preferences, which is garbage. It's not how you want to interact with something that you think is effectively sentient. It's like you want to tell, it's like when a human makes a certain chocolate chip cookie, you say, I don't like you to use the milk chocolate, use the darker chocolate, or mix them up a bit and do three-fourths, dark chocolate, 1/4, milk chocolate. And that doesn't change the overall recipe, does it? No, it doesn't. It just change is one of the ingredients. And so I think that's what we can see, is that because they have this sort of granular way of both outputting the models, essentially, it's reasoning, its outputs in these intermediate values. We also have a way to feed those things back into the system, and then if we store them over time, we're sort of codifying a behavior that becomes something that we see as a preference, we would see as a preference. So that's very cool.
Oh my gosh. And then, so, oh man, this has been very eye-opening, because now everything you just said applies to the Optimus bot. So
Yep.
I can see how other bot companies and other AIs that these bot companies will, engage or outsource to, they can do the basics. You can talk to it. You can talk to you back. You can tell it to do something. It'll know how to do that something. But it's this fine tuning that, and that all that data that they're going to have to be able to really, really, really understand every single scenario that could possibly happen.
Well, think about, and that goes back to my referenced article, which I did, the FSC Part 8, where I talked about, the Optimus version. What I'm saying in there is that they are building unified architecture here, and that very architecture, in other words, they are getting a lot of bang for their buck. In other words, they're doing things, right now it's a bit more like FSD is in the lead and Optimus is using the data formats, the data pipeline, the simulating framework. Obviously, it's now one team. That's something that's happened over the last couple of months. It's all been consolidated under Ashok, and you can bet money that the reuse across the system, after all, to go back to the very beginning of this, is we have a real world vision-based OS. Both objects, Optimus and your vehicle, are vision-based systems. That is the primary sensor input beyond audio and some other inertial management, et cetera. Obviously, their outputs are different, but Tesla have built a technique in the world of vision to figure out how to build a neural network that not only outputs well, does its evaluation well, has figured out that kind of secret sauce, but also knows how to output its intentions through these, we'll call reasoning tokens, and therefore, what happens on FSD will happen on Optimus, and then you'll see, probably as Optimus matures, a lot of the smaller nuanced things that happen on Optimus will be fed back into FSD. So it's really a virtuous circle of two different vision-based products kind of coming together, and clearly that allows Tesla to build other vision-based systems that are robotic, because really what we're talking about is building vision-based robotic systems, right? Like you could think of it like a drone or something like that, or a
Embodied AI,
it's an embodied
anything
AI.
with a camera.
It's embodied
Anything with a
AI
camera.
that's principally, yeah. And by the way, what's important to recognize here is it's not as if Tesla said, "Oh, we're a vision-only system." You noticed in Ashok's presentation is that he talks a lot about other data that comes to bear in that system. What's just noticeably absent are things like ultrasonics and lidar, and but essentially the model itself is doing sensor fusion. I mean, we have vision data, which is if you look at the box of data, if you look at those 2 billion input tokens, I don't know, I could do the math on it, but I'd say 90-something% of those tokens are vision tokens. There's audio data, there's the IMU, there's the routing data, there's kind of a reasoning loop data. So they are fully capable adding another input modality to the system if they deem it necessary, right? They've subtracted lidar because they thought it's not necessary, and I think the proof is here. But they certainly could add it back for some special purpose, like using this as a robotic docking system to the space station. I mean, they've done this in SpaceX, right? But they've done that in kind of more classic controls type of programming and not an AI, but they could probably take this AI and purpose it towards of that type of thing.
This is one of your most powerful shows that you've done. We
So much
love
fun.
every single one you do because you translate the technical jargon to things we can understand, and this was chock full of things. Ashok, of course, he's the man. He's the guy that did the whole presentation. He explained everything.
Read him
But
first. If you don't understand, go to me. And if you don't understand,
no. But my
yeah.
point was that it answered a lot of questions that many, both Tesla haters, but also even us, just didn't know yet for sure. This validated, right? Like, does it have memory? Can this actually be used for Optimus? People, they've said it a few times, but there's a lot of doubters. They said, no, FSD is nothing to do with Optimus. Does you need lidar? Is there a real advantage? Is there a real advantage with Tesla? Is there that simulation? Is there Tesla's real world simulation different or the same as others? Because if anybody can make simulation, and that was the answer, like, oh, we don't need your 8 billion miles, 6 billion miles of data history. We just need to use simulation and we're good to go. Well, not really, because you need your simulation to look like the real world, and yours won't. And then B, you need simulation. You need all that data to know all these little edge cases that you're not going to be able to simulate out. Just using simulation and AI to say guess the work.
Yeah. I think the upshot of this whole week discussion about is we've seen FSD 14 drop. We've seen a lot of testimonial from people with their videos and showing how the thing is remarkably better than 13 and has some, rough adolescent phase that it's going through as it matures to, catch up to the smoothness factors of 13. That's expected. It's completely normal from my perspective. We've seen that type of thing happen. Now we're reinforcing it with from literally the horse's mouth, in this case Elon, saying, hey, this is what we are doing, but that's backed up by Ashok saying, well, yeah, and here's sort of how we're doing it, here's the details, and I'll show you examples of these things in flight. And it makes you realize that this is a serious mature effort inside a company that has matured this AI in a way that solves one of the most difficult problems that we've been chasing in computer science for 30, 40 years, right? To build a natural system that does this. And by the way, in a sense, Optimus is a harder problem in a sense. And the fact that they are able to bring to bear all of this, the entire stack, and double purpose it into Optimus is such a great win for Tesla to have that opportunity to do that, because they're not starting from scratch and developing technique from scratch. They've got a lot of pieces of the plumbing in place. They got a lot of pieces of that data pipeline in place, and that's just an accelerant for them to either get to market faster or to effectively build a better product, or both.
Oh man. So I don't know if I'm right or wrong on this, but I was contemplating that I think that Ashok Swami, I think that Elon, maybe they deserve a Nobel Prize for what they've done here.
It's very difficult. I know from my years at Rivian and thinking about this problem when I was at Apple, it's a really, really hard problem. And it's they didn't stumble. They have tried a lot of they've hit a lot of dead ends at Tesla. That and Ashok's been there since the very beginning of this AI team, and they've hit a lot of dead ends, and they've learned what works and what doesn't work. And I think that's the thing that is missing in the discussion when you think about the competition showing up, snapping their fingers and saying, okay, here's the recipe, let's go. Sure, a follow-on team can copy and make progress quicker than a team that's really started in research mode and intertwined research and development over time. But you got to remember that there's a institutional kind of knowledge base and power in that Tesla team that just can't be replicated. There's just a knowledge set that's there in terms of not only what they've done, how they've done it, but how they thought about it and what they've thrown out. Like what we see here is a lot of what they brought in. We don't know all of the stuff they've thrown out and why. And we'll never know. But that's institutional knowledge that they have. And that means that they won't go down certain dead ends that other companies will be forced to go down because there's no way they don't have that memory.
Yep. Yeah, I don't think those guys care about the Nobel Prize, but I just think this is such an impossible problem that, as you said at the beginning of this, that you said at the beginning of this presentation, is solved. I think we all agree that it's solved. Most of us who are using FSD, Elon, and Tesla agree that it's solved. I mean, lots of nines to go. I'm not saying it's solved.
Yeah.
I'm saying that it's an impossible problem that people thought was never going to happen, and now we can see the line of sight. We're in the middle of the tunnel, see the light, and we're ready to. We know how to solve it. And he just explained.
Yeah, I think that's correct. We see, that's what I refer to as convergence, where we say we see where it is, and we can use present day terms like is solved because we can infer very quickly that there are only a handful, another decimal on the 9 that has to go, and that this is not, to say solved doesn't mean the finish line either. There's what's amazing about this is Elon mentioned it in that quote about a healthy, exciting roadmap. And that's what's amazing about these projects. And, I've been involved in many different engineering projects, is that when you get close to solving the main problems, all of a sudden, all these cool things open up, and that you're able to
possible.
You're able to approach the possible, where before you were just trying to get the very thing going. So, I mean, I saw that one of the reasons that I see this convergence occurring is because what's interesting about version 14 over 13 is version 14 for the first time starts to treat those small little problems at the end of the beginning or end of rides. I'll give you an example. They've solving the problems of gated parking garages, right? And how do they get through the gate and waiting on the gate? You don't chase the gate problem until you get the other stuff basically operating correctly.
Yeah.
And 13 kind of went there, and you notice that 13 doesn't have those tail ends or heads or tails. They don't have those pieces. They don't have those components. But 14 is starting to layer them in. They now have a roadmap, because the roadmap isn't now solve FSD. The roadmap is make it better, make it more sentient, make it smarter, and make it deal with a lot more driving conditions that are very very important to solve, but haven't been solved in the previous version.
Yeah, some and straightforward, right? You're standing there and you're telling the car, wherever it's parked, come to me. Okay, it can do that. Just be sure it's safe. Banish is a lot more. Okay, what do you mean by banish? Drop me off at the front. Okay, I'll drop you in front of the Target store. Now what? Well,
where do I go?
Do I drive around? Do I park at the closest one? Do I park as far away? Do I go to the next parking lot? Is that safe? These are the things that this car, he said that this car will be able to figure this out, because it's got reasoning. When the reasoning comes, it'll know, what, I can't park in the near front. I'll have to park further, but I know that you don't like to walk, something like that, whatever. So it is much more, you have to have an intelligent system to be able to do proper banish.
It's essentially the way to think of the system as it evolves in either unsupervised mode for our own personal cars or robotaxi is literally like you've hired a chauffeur,
right? And
it is your chauffeur. You've taught that person what your preferences are, what your likes, your dislikes, what you're willing to do, and that person grows with you. And unlike a chauffeur that appears only in one car, the chauffeur just runs in every robotaxi. So it doesn't matter where if you get off, get out of the airport in Paris, France, and you get in a robotaxi, it knows what your preferences are.
But when you and I go to Austin and we hail a robotaxi, it's going to be my chauffeur, not yours, Phil.
That's right. That's okay. You get to pay.
Yeah, the cents per mile, I'll take it.
Yeah.
It'll cost it'll cost less than the beer that you're going to buy me. So, Phil, you're awesome. This is it. This is why we turn to you. You've done this. We've done many shows. I think we pretty well do one a month. And each time you explain something very important about Tesla's autonomy, FSD, their technology, the software. You actually ran the software division at Rivian, from scratch, trying to help figure out how that company should install, software stacks in the vehicle. So you understand to some extent, what's going on, and you dive deep. Appreciate you explaining everything that Ashok explained. I will put the link to the article that Ashok did up, and as well as the YouTube video that he did. If you have the technical chops, watch that, because he does a great job as well, of course, explaining to people, the public, what Tesla's doing. But this show with Phil did a fantastic job of taking the parts that Ashok explained, and he explained it to something that even I can understand. So thank you, Phil. And I shared here earlier, this is, follow him on X at PBEISEL, Phil Bisel. Elon responds to him quite often, and he appreciates all your articles. And so here's a bunch of articles he's already written.
You know what
and
I've
more.
noticed? I noticed that he likes a lot of things, because likes on X now are private.
Yes.
And I get a like on every 5 posts from him. I don't think some of the things that I say he wants to put his name on and make public, because they seem, like we've coordinated efforts or something. But, he'll say, oh, I like that. And I'm like, well, I can't advertise that, because, what goes on in like club stays at like club. So,
So you should not share that. No. You can share it to me. DM it to me. All right, buddy. Thank you so much.
All right.
Thanks,
Thank
everybody. Bye-bye. I've created a website that is the most comprehensive resource for the Tesla investor. Please check it out. Simply go to my website at herbertong.com.